So you guys are working with the gravitational, electric, and magnetic fields. Now what we're going to do is we're going to get into what I often call a little unit called fields 2. There's no such thing as fields 1 and fields 2, but I just call it fields 2. And it's actually a modification of electric fields. Now, if we go back to what you guys with basic electric fields, you guys did stuff like, if you've got an electric field and you take a charge and you put a charge inside the field, that charge will then just follow the field. Whether it's positive or negative, it'll go with the field or against the field. It goes with the field. Now, what if instead, what you could do is you could take the electric field and you could change the direction of the electric field to go any way you want, something like this. And then, of course, what would happen is whatever little charge you have, that little charge would then follow the field and move from one place to another. Well, this is literally the idea behind circuitry, because that's what wires do. Wires and cables and conductors take the electric field, contain the electric field within their structure, and then the charges that flow along, the electrons for electricity specifically, then follow the direction of the electric field that is guided and redirected by the wires. And that's the basis behind electricity. So that is what Fields 2 is generally about. Fields 2 is about the general properties, nature of electricity and electronics, and producing electricity. Now, so this is what I often call Fields 2. So we're going to start looking at Fields 2, and basically this is circuits. And electricity is basically what is it about. Now, the great thing is a lot of this actually connects to what you guys did in grade 9. So a lot of this, especially the first part, is going to be all grade 9 review. And it's really straightforward. And compared to Fields 1, typically this stuff is way easier. So we're just going to kick back and look back at what you guys did in grade 9 and review some of the ideas from grade 9 and connect it to some of the field stuff that you guys have done. So for Fields 2, basically the idea is contain the electric field in wires, and this is what actually directs charge flow. Now, of course, more specifically, it's the electrons, because you got the electrons going from one place to another. And of course, this is the basic idea behind electrical current. The symbol for that, of course, is a capital I, and this, of course, is flowing electrons from one place to another. Okay, now, if you remember from grade 9, there's two typical types of current. The whole flowing electrons, this is what's often referred to as actual current, but there's another idea out there that's actually flowing positives, and this is what's called conventional current. Because I guess when they all started doing this way back when, they thought it was positives going from one place to another, and then they eventually found out it was negatives going the other way. But instead of flipping everything, they just talk about conventional current and actual current. So if you talk to most people about electronics and you ask them which way does electricity go, they'll say it goes from positive to negative. But why would an electron want to leave a positive terminal and go to a negative terminal? It doesn't make any sense, because that's the conventional current idea. Regardless, it doesn't make that much a difference. Positives going one way, negatives going the other way. It's all the same thing. So anyway, so this sort of defines what current actually is. It's often referred to as the change in Q divided by the change in T. It's the rate of charge in a circuit or electronics and that type of stuff. And that's where the fundamental idea behind current came from. Now, of course, in order to move charges from one place to another, you need to have a force or a reason for them to go. And this is where a term that comes up called electromotive force kicks in. And this is often referred to as EMF. And a lot of people think EMF stands for electromagnetic force. It's not. It's electromotive force. So here, let's clean that up a little bit. Electromotive force. So it's literally electron motion force, sort of. So electromotive force, or EMF. You'll often see it as not only just EMF, but sometimes it's also written as very script fancy E. And this is what moves from one place to another. This is often also referred to as potential difference, which is the basic voltage stuff that you guys have done. So it's, you think force, think it's not newtons, but most people just go with potential difference, and it's a form of voltage. Okay, so there's different things you guys did with this in grade 9 as well, but I mean, there's different sources for EMF. For example, you guys looked at, there's chemical sources like in batteries, there's electromagnetism, there's even piezoelectric, where if you crush certain crystals, they give off little bits of electricity. There's like solar power. There's a whole bunch of different ways to create this EMF or electromotive force or potential difference in order to get charges to move from one place to another. Okay, so current was a basic quantity you guys took way back when, especially if you've done more electronics and stuff. Everybody knows about current. And then you've also got the voltage or the EMF that we'll look at in a little more detail a little bit later on. Those two things. Now, those two things are often tied together with a couple other quantities. One of the other really common quantities out there that they're connected to, one of them definitely is resistance. And of course, most people know about resistance. You guys do some work with resistance in grade 9 in electricity as well as electronics. But most people know about resistance, and of course, this is where Ohm's law comes in that you guys do in grade 9, where resistance is V over I. And if this value is constant, then the resistor is what's referred to as ohmic. So typically you want resistors to have the same resistance, and if they do, they're called ohmic. If they're not, then they're not considered ohmic. And if you sort of plot things out, if you do like a little V current graph, typically as you increase the voltage or EMF on something, you should get more current, and you want a straight line. And if it follows a straight line, that slope is your resistance, and it will be ohmic if it's nice and straight. Now, not all things are straight lines. For example, like heating elements and stuff like that, and light bulbs, the old-fashioned incandescent light bulbs, they get hotter, then a resistance goes up, they're not ohmic. So different things follows Ohm's law, some things don't. But voltage and current and resistance are probably the three more common quantities that were used and shown to you, especially in previous electricity and electronics type stuff that you guys have done. Okay, so let's work on this a little bit more and expand a couple things and bring in some other quantities that kick in as well. Another common quantity that kicks in with this stuff is power. We'll get to that as well. And we'll look at a little more resistance type ideas and see if we just get some other ideas going too. So first things first, let's look at just resistance a little bit more and what that actually is about and stuff like that. Now, when some people think about resistance, they often just think about like actual resistors themselves, but there's resistors which are used to control flow and stuff. These guys often, control or they'll limit the current. There's also what are called loads, and loads are a little bit different. Often these guys are meant to use up energy and slow things down. For example, like an electric motor or a light or stuff like this. These guys often have some form of target energy that they're trying to do. So resistance isn't just about resistors. It's like motors, the lights, speakers, anything that's being used that's taking energy and using energy, often a target form of energy, and sometimes those are called loads. So, you have a basic circuit, you can have a resistor in there to control current or limit current, that kind of stuff, but maybe it's hooked up to a light bulb. Well, that light bulb is also a resistance, but it's more often referred to as a load than anything else because it actually is doing something that you want. You want it to use up some of the energy, okay? Now, another quantity that often kicks in, and we mentioned it just a little while ago, and definitely connected to resistance is good old-fashioned power. So power is often associated with resistances and loads, and it's basically how fast the actual energy is actually used. It's actually the rate of energy use. So power is actually, you'll often see it written as the change in energy divided by the change in time is what you'll often see. Now, the thing is, if you look at energy, and this actually kicks back, this is where your fields 1 really kicks in. If you calculate the energy, the potential energy, or just the energy in general of a charge in an electric field, and of course there's an electric field in the wire, energy was equal to Q times V, which is the potential difference, and that's divided by time. But Q divided by T, that is your current. So you'll often see power written as current times voltage. So not only is current voltage really, really commonly used in Ohm's law to find resistance, it's often definitely connected to power. And often the Ohm's law, because we have Ohm's law from before, resistance is equal to V over I, or just rearrange V is equal to I times R. These two expressions are often spliced together for power. For example, you can solve for power using current times voltage, but you could actually substitute this in for the V, and you've got I times R, which gives you I squared R. You can also rearrange this for the current here, which would be V over R. So that could be V over R times V, which gives you V squared over R. So these are all common ways that power is calculated, and it has a huge connection to resistance. The two quantities that are most important, the I and the V, are in both of them, so they often feed off each other. So power and resistance are awfully connected to each other in different ways. Okay, now resistance doesn't just come from resistors and loads. It also comes from what's called internal resistance. It's also in things like the wires and stuff like that. Now wires, of course, they have resistance in them. You have to push through, and different things like the length of the wire is important. You want wires to be as short as possible, not to mention the width of the wire. Basically, the thicker the wire, the bigger the cross-sectional area, the more room there is to go through, so that actually brings the resistance down. But also the material is important, and this is where a quantity called resistivity actually kicks in. Different metals, because of valence electron structures and how the atoms are put together, some metals let electricity go easier than others. And sometimes you'll see the expression that the resistance for a wire is rho L divided by A. That rho, that's the symbol for resistivity. The length of the wire, of course, is length. That's the L, and that's the cross-sectional area which connects the width of the wire. So basically, there's also resistance in wires. You don't always forget about the wires. You want wires to be as short as possible, also be as wide as possible, and they may be made of a really, really good material. Okay, that's why for jumper cables for cars, you can't just use little tiny skinny wires. They have to be nice big wires so lots of current can get through. You also don't want them too long though, so the current can get through. Okay, so there's all these different things that kick in, but you got to think of, a lot of people think resistance, they think just resistors. Well, it's not just resistors. There's loads, where the energy is being used for something you want. There's power involved, and they're definitely heavily connected. But also there's always resistance in wires as well. There's internal resistance within the wires, and those things all sort of connect together. Okay, so these are some of the basic quantities and basic ideas. Some of these are from review from grade 9 and from electronics and science classes and stuff like that. But we'll practice this a little bit, and then we'll incorporate into circuits as well and build on it with some other stuff.